Let me uh, let us discuss wave function position and momentum space. Okay. Consider an athlete in a 100-meter race. This is the starting point and this is the finishing point. He's running and here he has no velocity, so zero velocity, and he's gaining his maximum velocity here, and the corresponding momentum is p1, and the velocity is reducing when he reaches here, and this is the corresponding momentum is p2. With this p2 momentum, he is running from here to this much distance, and then after he's running with another velocity and the corresponding momentum is p3. Okay, so I'm drawing a graph versus graph of probability, momentum versus the probability of the momentum of an athlete. Okay, so if I'm writing here P1, P2 and P3, most of the time he's in a momentum P2. So the maximum probability of the momentum of an athlete is P2. So I can draw a graph. You can draw a graph like this. Okay, you can draw a graph like this. And I'm denoting this term phi as momentum wave function. Momentum wave function. Then consider a midfielder in a football ground. This is a football ground. Okay, this is the middle portion. And this x-axis 0 around 50 meter. So I'm drawing an axis. The probability of his position, I'm denoting it as mod psi square. Probability of his position of midfielder. He can come to here, he can go here, but the probability of finding him is maximum at middle portion of this ground, football ground. Okay, and I'm representing the term psi as position wave function. Position wave function. Here the probability of momentum I'm finding, and I'm denoting phi as momentum wave function. Here I'm finding the probability of the position of a footballer, that is mod psi square, and I'm stating psi is the position wave function. Okay, wave function means if you are considering an equation y equal to x square. If I'm giving x equal to 2, I'll get y equal to 4. This is a function. This is a function of x. When I'm giving an input, I'll get an output. Okay, that's a function. So the position wave function or momentum wave function, generally wave function, is also like that. If you are giving some input, we'll get an output. Okay, I'll elaborate it. The wave function, one part is wave and another part is function. Let me consider an electron is moving in x direction, and the electron can move from point A to point B. Okay. In the y-axis, I am drawing a wave function, a position wave function psi, and this is the electron. It's moving to and fro. And I'm drawing a wave function as like this. Wave function like this. This is psi. Okay. Then I'm drawing another graph. This is x. This is position A. This is position B. And this is mod psi square. Mod psi square. So this is a sinusoidal function. If I take the square, if I square it, then I'll get a function like this. Okay. This represents, this is a wave function. This is a sinusoidal wave function. And representing as psi of an electron moving in a one-dimensional space. And this is mod psi square. Mod of the square of the mod of the wave function. This means that this is maximum at this point. That means that I can find the electron. The probability of finding an electron is maximum at this point as well as this point. The probability of finding particle is minimum at this point and this points. So we can define wave function like that. Okay. I'll elaborate it. So, first of all, let us discuss position space wave function. Consider a one-dimensional space. An operator x is operating on a state get x dash, position get x dash, and we will get an eigenvalue x dash and get x dash. Let me denote orthogonality condition also. X double dash, inner product of x double dash x dash equal to delta of x double dash minus x dash. We have discussed it earlier. Okay. And a state get alpha can be represented as integral dx dash outer product of x dash alpha. The value of this term is equal to 1. So we can represent any state get, any get like this. Okay. And the term mod of x dash alpha whole square dx dash is the probability for the particle to be found in a narrow interval dx dash around x dash. Okay. This term is actually the expansion coefficient. X dash alpha is the expansion coefficient, and the square of the mod of that expansion coefficient is the probability for the particle to be found in a narrow interval dx dash around x dash. Okay. And the term x dash, inner product x dash alpha, we can call it as wave function, and we are representing this x dash alpha as psi alpha of x dash. Earlier we had told the probability of finding the particle or probability of finding a midfielder at a particular position is the square of the wave function, square of the mod of the wave function. And wave function is defining, and the position wave function is defining. First of all, the position wave function is defining, that is psi alpha of x dash equal to inner product of x dash alpha. Okay. Let us consider an inner product of beta alpha using the completeness relation x dash, completeness relation of x dash. That is beta alpha we can represent as integral dx dash beta x dash outer product of x dash alpha. This is integral dx dash outer product of x dash equal to 1. So we can represent beta alpha in this format, in this form. So this beta x dash is, we can represent as psi beta star of x dash, and this x dash alpha we can represent psi alpha of x dash. That is beta alpha, inner product of beta alpha represents the probability amplitude for the state alpha to be found in state beta. The probability of state alpha to be found in state beta can be represented as beta alpha is known as probability amplitude. Okay. And next, we are deriving form of position operator. Okay. So for that, let us examine how beta A alpha can be written using a wave function. Okay. So beta A alpha equal to integral dx dash, integral dx double dash, beta outer product of x dash, A outer product of x double dash alpha. We know by completeness relation dx dash, integral dx dash, outer product of x dash equal to 1, as well as integral dx dash, outer product of x double dash equal to 1. So we can write beta A alpha in this format. Okay. And that is equal to dx dash, integral dx dash, integral dx double dash. This term is psi beta star, and this term is psi alpha star. Beta x dash is, sorry, this is beta x dash is psi beta star of x dash, and x double dash alpha is psi alpha of x double dash. If A is the function of the position operator x, then we can give A equal to x square. Then we can find out x dash, x square, x double dash equal to x square is operating on x dash, x square is operating on x dash. So we will get x dash square. This is an operator operating on x dash. We will get x dash square and inner product of x dash, x double dash. This we know what is inner product of x dash, x double dash. That is delta of x dash minus x double dash. Okay. So we can write beta A alpha equal to integral dx dash, integral dx double dash, psi beta star of x dash square, delta of x dash minus x double dash, psi alpha x double dash. Okay. And this term we can write in this form, integral dx dash, psi beta star of x dash square into integral dx double dash, delta of x dash minus x double dash, psi alpha x double dash. Okay. This we will get as psi alpha of x dash. Let's check how. Integral dx dash, delta of x dash minus x double dash, psi alpha of x dash equal to integral dx double dash, delta of x dash minus x double dash we can write as delta of x double dash minus x dash. This is the property of delta function into psi alpha of x double dash. Okay, that is equal to psi alpha of x dash. How? Let us check how. Since integral dx of delta of x minus a f of x, this is the property of a delta function, equal to f of a. Okay, so this is in the form of this property of delta function, and we can write beta A alpha as integral dx dash psi beta star x dash square psi alpha x dash. Okay, psi alpha x dash. In general we can write beta f of x dash. This is the function of x dash. This is the function of x dash. Beta f of x dash alpha equal to integral dx dash psi beta star of x dash f of x dash into psi alpha x dash. Okay. In left side it's an operator. In right side, it's not an operator. Okay, so we are defining in position basis, in basis of x dash. How can we write a position operator? If position operator is a function of x dash, we can write that function of x dash itself in this integral format. Okay. Then we'll check in the position basis how momentum operator is operating. Okay, in momentum, what's the format of momentum operator in position basis? Here we have verified what's the format of position operator in position basis, and here we are going to explain what is the form of momentum operator in position basis. We know the momentum operator, infinitesimal translation operator, that is shifting one particle from one point to another point because of the momentum, and that infinitesimal translation operator we are taking as 1 minus ip delta x dash divided by h cross is operating on a state alpha, that is equal to integral dx dash. This infinitesimal translation operator we can write as t of delta x dash, and alpha we can write as integral dx dash outer product of x dash alpha. Okay, this is by using completeness relation, and this we can write as integral dx dash x dash plus translation operator is translating this state into another state x dash plus delta x dash into x dash alpha inner product of x dash alpha, and this we can write as integral dx dash x dash into inner product of x dash minus delta x dash alpha. This step we have discussed earlier, how this we can write in this format. Okay, that is equal to integral dx dash into x dash. We are writing this term as inner product of x dash alpha minus delta x dash into dou by dou x dash of inner product of x dash alpha. Dou by dou x dash of x dash equal to 1. This we cannot write as a ket. That's why we are writing this step is in this format, in this form. Okay, and that is equal to dx dash outer product x dash alpha minus integral, just expanding it, integral dx dash x dash delta x dash dou by dou x dash inner product of x dash alpha, inner product of x dash alpha. LHS we can write 1 minus ip delta x dash divided by h cross operating on alpha as alpha minus ip delta x dash divided by h cross alpha, that is equal to this term is alpha minus integral dx dash x dash delta x dash dou by dou x dash of inner product of x dash alpha. Okay, we can compare both sides of this equation. This alpha equal to alpha, and the next term ip delta x dash divided by h cross alpha equal to integral dx dash x dash get x dash delta x dash dou by dou x dash of x dash alpha. Okay, and the both side there is delta x dash term. This delta x dash term we can take outside of this integral because this is a finite distance, it's a finite value and it's a constant value, so we can take it outside. That's why this got cancelled. So this implies P of alpha, P ket alpha equal to integral dx dash x dash minus ih cross dou by dou x dash alpha. Okay, or x dash, if you are finding x dash p alpha, that is equal to integral dx dash x dash inner product of x dash into minus ih cross dou by dou x dash of x dash alpha, that is equal to minus ih cross, we can take outside integral dx dash. This we can write as, just for sake of this equation, delta x dash minus x dash. This will become, this is equal to 0, but we can write in this format, that is dou by dou x dash alpha. Okay, that is in the form of integral dx delta of x minus a f of x, that is equal to f of a. So we will get as this is of f of x. So we will get instead of this a, here it's x dash, so we can write f of x dash. Okay, that is minus ih cross dou by dou x dash of dou x dash inner product of x dash alpha. Okay, if we are taking x double dash instead of this alpha, we will get x double dash px double dash equal to minus ih cross dou by dou x dash inner product of x dash x double dash, that is equal to minus ih cross dou by dou x dash of this x inner product of x dash x double dash. We have solved earlier that delta of x dash minus x double dash. Using this equation p alpha, using this equation, we are taking beta p alpha, we will get integral dx dash inner product of beta x dash into minus ih cross dou by dou x dash of inner product of x dash alpha, that will become integral dx dash, this term is psi beta star of x dash. Okay, this term is psi alpha of x dash into minus ih cross dou by dou x dash. Okay, or minus ih cross dou by dou x dash of psi of x dash. So we got both the form of position and momentum operators. That is, position operator in position basis is in the form of f of x dash equal to f of x dash itself, and the momentum operator in position basis is in the form of minus ih cross dou by dou x dash. Okay, and the properties of this operator, the form of the operator is and the properties are x dash pn alpha equal to minus ih cross whole raised to n dou n divided by dou x raised to dou xn of x dash inner product of x dash alpha, and this property beta p raised to n alpha equal to integral dx dash psi beta star of x dash minus ih cross whole raised to ih cross raised to n dou n divided by dou xn psi alpha of x dash. Okay, and we have discussed position space wave function. Okay, position space wave function. We told earlier that there are two wave functions, position space wave function and momentum space wave functions. In the previous discussion, we have discussed position space wave function. Here we are going to discuss momentum space wave function. So for momentum space wave function, if an operator P acting on a ket P dash, we will get an eigenvalue P dash into ket P dash. Okay, inner product of P dash, P double dash is equal to delta of P dash minus P double dash, as we have seen in position operator. In momentum basis, we can represent a state ket alpha as integral dp dash outer product of P dash alpha. Okay, this term is equal to 1 by completeness equation, and this is P dash alpha is expansion coefficient, and the square of the mod of the expansion coefficient in a small region dp dash is the probability that a measurement of P gives eigenvalue P dash within a narrow interval dp dash. We have earlier discussed about an athlete running in a 100-meter race. In that, this we have represented as a wave function phi, and this probability of finding him in this particular momentum as mod phi square. Okay, in a small region, if this is in a small momentum region, we can represent in this form. So the p dash alpha, this is the momentum space wave function. Momentum space wave function we have represented in that athlete's example as p dash, inner product of p dash alpha we can denote as phi alpha of p dash. If alpha is normalized, we obtain integral dp dash alpha p dash alpha equal to integral dp dash. This term is equal to mod of phi alpha p dash whole square, that is equal to 1. And here we are going to discuss connection between x representation and p representation. To transform from x dash to p dash, we need a function of x dash and p dash. To transform from position basis to momentum basis, we need a function of x dash and p dash. Function of x dash and p dash, that is known as transformation function x dash and p dash. And we are going to derive the form of this transformation function, how this transformation functions will look. Okay, so that is form of transformation function x dash p dash. We had derived x dash p alpha equal to minus IH cross dou by dou x dash. Okay, this P operator is minus IH cross dou by dou x dash. We have derived the form of this operator as minus IH cross dou by dou x dash. So we can write x dash P alpha as minus IH cross dou by dou x dash alpha. Letting alpha be a momentum eigenget P dash. If you are taking momentum eigenget P dash in this position, we will get x dash p dash equal to minus IH cross. So this is left side, this is right side. Right side we will get minus IH cross dou by dou x dash of x dash alpha. Instead of alpha we can write get p dash. Okay, that implies p operating on p dash, we will get an eigenvalue p dash into x dash p dash, inner product of x dash p dash, that is equal to minus IH cross dou by dou x dash of x dash p dash, inner product of x dash p dash. Okay, that implies minus IH cross dou by dou x dash, inner product of x dash p dash minus p dash x dash, inner product of x dash p dash equal to 0. We are writing this equation as a first order differential equation. And we can write it as that implies dou by dou x dash of x dash p dash minus ip dash divided by h cross x dash p dash equal to 0. Okay, this is a first order differential equation, and the solution to this is first order differential equation. This is the first order differential equation. Solution is x dash p dash equal to n e raised to I p dash x dash divided by h cross. Okay, where n is the normalization constant. I am not deriving this equation. You just apply this equation in apply this value of the x dash p dash here. You will get you can find out this equation is right. Okay, so the solution of this equation is n e raised to I p dash x dash divided by h cross. This is the equation of a plane wave. Okay, this is the form of equation of a plane wave, and n is the normalization constant. And x dash p dash is the probability amplitude for the momentum eigenstate specified by p dash to found at position x dash, or it is known as momentum eigen function in x space. Momentum eigen function. Okay, this is known as momentum eigen function. To get normalization constant n, we have to find out what is the normalization constant n. We can write x dash x double dash equal to integral dp dash x dash p dash outer product of p dash into get x double dash, okay, by completeness relation. That implies left side we can write delta of x dash minus x double dash, that is equal to, and the right side is integral dp dash n e raised to I p dash. This is x dash p